First of all, I'd like to know, like, we already heard a lot of people here don't support QKD, but how many of you actually feels QKD is not worth spending so much time and money? Okay, so I guess I think
maybe more people will commit if so is quantified so much.
Well, at least here in Europe, people are spending billions of euros for QKD, because I personally feel that after source algorithm, we have not seen any other algorithms which provide, or practical algorithms which provide exponential advantage. So if you want to write a research proposal, you write QKD as an application because it claims to have conditional. Yep. Yeah. It's a discussion. That's fine. We can continue during coffee break.
This is a completely opposite picture in the US, because if you mention QKD in a proposal tool, really anywhere except for NSF, your proposal gets dinged.
Okay.
So I think in Europe, they're spending billions on quantum computing, but not on QKD. I would be surprised if it's anywhere near that level. I don't know the exact, it'd be interesting to see the amount of funding, but also there are companies who are making money off of QKD right now. So
yeah, I think there are a lot of companies. But I don't know the exact amount. I have seen BSI papers on their stand on QKD. They are strongly supporting it. And what Professor Andreas Winter also told during yesterday's lunch break, that most of the QKD hardware that they are developing can also be used in other applications as well. So they use this concept as a backup for it. But if a lot of you don't support QKD, do you believe that post-quantum cryptography will be broken in near future, or say sometimes in a couple of decades? So what will be the solution if there is no QKD and no post-quantum?
I mean, my understanding is we will want to have what's it called, asymmetric and most likely hence public key cryptography anyway. Like, I mean, QKD solves a specific cryptographic problem from antiquity, but for the modern world, it's just a small section. So we need it anyway. So the existing post-quantum protocols, I mean, as far as I know, there are different proposals of actual hard problems, supposedly hard problems, and algorithms to do post-quantum cryptography. Any of them may be broken because we have so little experience with it. I mean, the RSA is fantastic because we had thousands of years of mathematical study of the factorization problem, and so that created a lot. I mean, I think for the post-quantum, we are much more at the beginning, and so some of them will be broken. But I think complexity theorists will be very confident that some such thing exists, for the simple reason that they don't believe, for example, that quantum computers are going to solve NP hard problems, and so they're most likely there will be also trapdoor problems and what not. We just have to discover them, and that may take time. And I totally think it's worth it. So,
if I may, there is different post-quantum secure primitives. These are what we call like the basic building blocks. These have been used for a different amount of time. Psych, the breakage of psych, is often cited as a problem of post-quantum cryptography. It's not so much because everybody in cryptography kind of knew psych was a bit shaky because it was very new. So nobody was surprised when that was broken. Rainbow was a bit different of a matter. What we do have is we have robust combiners that you can use to combine two crypto systems into something that is secure, even if one of those holds. And there is one algorithm that's been used that's been invented in the 70s, in the 1970s, that's called classic McAleese. And Rosenpath actually uses classic McAleese internally. For us, it's fairly efficient because the ciphertexts are small, the public keys are giant. But if you really want the highest level of security, you can use 2, 3, 4 of these post-quantum algorithms in concert and you can combine them securely and redundantly. So for the highest security setups, always do this. You're going to pay with a bit of reduction in efficiency, but it definitely can be done. So redundancy.
Okay, now let's go back to the physical layer.
Okay, yep.
That's where the quantum stuff starts.
Okay.
And where we wanted to add a bit of
Yep.
accuracy to the discussion on the aspect of hardware attacks, because one thing we want to understand is in which direction to go with the quantum research.
Okay, so I don't know if the slides are included, but yeah, like Professor Winter told that asymmetric cryptography, which is needed, is not currently solved by QKD itself. And one of the example is authentication. There are some devices like physically unclonable functions which provide hardware security. It's not based on a protocol level or mathematical security. Might be useful. I don't know how many of you are aware of physically unclonable functions or other hardware security things which can complement QKD in terms of providing security for asymmetric cryptography. So if you, I mean, you know a lot about PUF, so maybe you can introduce it.
Yeah, I think paths are still used. Classical paths are already used, but there's also the question of reliability. And we start research on quantum paths. That's the very beginning. There's also this big project we have, this grand challenge of quantum information theory, where the people try to develop some kind of quantum paths and think about this. And we make now the first steps to show that we can use quantum mechanics to make this physical unclonable function working. So that's, of course, an alternative. Is there a talk about this, you say? Or?
Yeah.
Okay.
I'll introduce
you will
physically unclonable functions, but other hardware primitives that can complement this kind of protocol security.
So I would take a little bit different approach to all this. And I mean, first off, I would argue that massive investment and all the interest and energy into this is really driven by quantum computing. And there's really good reasons why. So quantum computing is not going to solve everything, but there are many problems that it's able to do, and simulation and things that will be major advances when we get to that level. So you have this infrastructure being built around quantum that has unique capabilities. One of the things that you can do that's really interesting is that you can share, or you can create keys between people at distance, and if someone tries to intercept it, you can detect that they intercepted, and you have these quantum characteristics, right, that we're exploiting for QKD. You might exploit it for other means as well. I guess to me, it's, well, first off, there's reasons for looking at low photon count or single photon communications, because I need to build it up for quantum computing. So I would turn it around and say, if you have all this quantum computing stuff, and we heard it said that QKD is expensive. I mean, that's like saying in the 1970s, well, computers are expensive, I shouldn't invest in computers, and arguing that we don't have QKD in our cell phones. Well, we didn't have computers in our pockets either back in the 1970s, right? So, I mean, this technology is going to come down in cost. It's going to be mass produced at some point in the future, and what that's going to look like and exactly what it's going to do, I have no idea, right? And all the problems it's going to solve. But we have this kind of unique resource and this technology supply chain that's being developed. Are there useful things that we can do with that for encryption and security and these other problems, is what I'd say.
Yeah, but I'd like to ask some follow-up questions if no one wants to say right now. Yeah, so QKD, like we know, and Caroline also pointed out that cryptography is now interdisciplinary. So QKD just solved the physical layer of problem, but we have multiple layer over it. Carol also introduced OCI, that we have something like a lot of application layer, but apart from the physical layer, it is still protected by the classical cryptography. So if the top layers can be hacked, is it beneficial to invest so much time and effort to develop the bottom layer? Because you can hack the top layer and get the secure key bits, basically.
See if there's interesting things that you can do with it. And so if we do hybrid approaches, we get some extra security there. And as the technology develops, we'll be able to do more. And I think it's still an early technology and we need to see where it goes, right?
For example,
So I
simple-
agree and disagree with you, Dan. I agree in that the growth in the interest in quantum computing and building of all those technological supply chains, as you have said, is very important and does present a lot of opportunities for everyone to do productive research using those things and using those ideas, and perhaps testing some of these new security schemes. At the same time, I don't view security as monolithic. It has to be customized to a task, and I think there are many niches of security, security science, I guess, where various groups can fit in. For example, if you have, as was shown on the slides by the Rosenpass, there was a slide with all the QKD links that are secure fiber. Between them, there was blank white links. In China, that would be the secure, physically secure, trusted nodes. They have, soldiers and such guarding those installations. Do we get rid of the? Does QKD solve the problem of having soldiers around? No, it does not. Does standard encryption solve a problem? No, it does not. You have to have different layers of security, including physical security. So there's all these niche problems, and I think that the opportunity is there to use the new devices that we're getting to study them, so I guess we should not just be trying to have QKD or really any other solution solve everything. We should have it solve certain problems, and identify those problems actually very interesting.
Perhaps just a small comment. I think we should also take care somehow of the money, because the question is always how much would a normal user spend for security? If you say you can have a very fast internet, but it's unsecure, but it's you don't have to pay so much, perhaps most people will buy this. So, that's the question: how people are there, how much money do they have, how much money they will spend for security. Of course, if you have government and such things, it's very important to have it. But for normal people, I think it's very hard to make commercial for security sometimes.
Okay, so I have now, I would like to say something, but let's get to the physical layer security part, because I at least from my side, there's one fundamental question, which is about the modeling of physical layer security. Can we even come up with physics models that allow us to give a theoretical proof of the system based on the assumption of Maxwell's equations or some Hamiltonian or some laws of quantum mechanics? I think that's, if you look at the size of the systems and the amount of atoms in it, it's quite a daring question. And maybe we, just to get everyone on one page, we look at one or two examples of how actual QKD system implementations can be attacked.
Okay, yep. So basically, we have seen a lot of mathematical proofs for QKD, but while implementing, we face a completely different sort of challenge. We don't have a perfect single photon generator. We use weak coherent pulses, which creates multiple photons, and that can be exploited for photon number splitting attacks. There are other attacks in which when the system reads a signal, a photon, it reflects back some signal, which can be used to gain the information about the key, which it's clicking 0 or 1. There are other hardware attacks, like when Eve try to send a signal to the device and it observes the reflected signal, and based on that, it can guess what key is with significant probability. I mean, there are multiple types of attacks, and I think BSI summarized this. Currently, they are focusing on 49 types of hardware attacks that are possible, and they only have countermeasures for 18 of those attacks. So there are still a lot of side channel attacks which requires new creative countermeasures that we don't have yet. So right now I feel like we have the mathematical security, but the question is, will we ever have the implementation security? Because we need a perfect device here.
Can I ask you, how close do you need to be to the QKD devices to perform these attacks you just shared with us?
There are, I don't know, for example, photon number splitting, you don't have to be close to the device. You just wiretap the signaling, maybe the broadcast signal or the fiber signal. But for other like backflash, you need to be significantly close to the device, similarly to the Trojan horse attack. But these are some examples. And fake state attack, you don't have to be close to the device because you send the signal to the device to block the device to measure in certain basis. So you can send the signal from anywhere. So there are some attacks which requires you to be close or within the same room, but some attacks can be done from the far.
So I guess the information, the quantum information, like it remains quantum information, and at some point it returns to being classical information, and then you use these. So are these attacks that operate on the quantum information level, or are they operating after the information was turned into classical information again?
Yeah, I think when it turns into, like, this is a different type of attack where they blocks fake state attack. They block you to measure in a certain basis. But so this backflash attack, it happens when you measure the signal. So when it turned into the classical signal. And photon number, it occurs during transmission, which is the quantum phase. So for QKD, this just while transmission, that's the only quantum phase. Then you store the key where it can be attacked. That's completely classical. So I think most of the attacks are on the classical side of the algorithm. But so, for example, photon number is while transmitting, so I can say it's quantum.
And that one basically works because the quantum key distribution here is imperfect because it transmits multiple quantum states with multiple photons. So we think it should be secure if there was just one photon.
Yeah, if we have ideal hardware devices, then it should be technically secure for this case. But for other cases also, we need very ideal hardware devices that stops any signal going out of the device.
That was enlightening. Thank you very much.
But again, even in device-independent QKD, I've heard from people that they cannot ever stop signaling going out of the device. So you can protect as long as the signal is quantum, but once it turned into classical, there is a probability that some signal can go out of the device, and it can be attacked when the signal turns into classical.
Yeah. So is there a version of this where you include entanglement-based QKD?
So this is the chart from BSI. They analyze different attacks, but they have not considered entanglement-based protocol. They focus on prepare and measure because it's easy to implement, and I think they are considering BB84 or decoy state BB84 as one of the standard protocol for QKD.
Yeah, it'd be interesting to see that for entanglement. Yeah.
So for the standard protocol, I would also like to ask, like, as a user of a device, like you use your phone, you don't know what's going behind it, and you trust it to be secure. What sort of standardization you need for QKD to trust it, at least to some level? Like, we know how to standardize PQC, but for QKD, what sort of standardization do you need? What sort of standardization do QKD hardware manufacturers should implement so that you can trust that it is secure to a certain level?
I mean, as far as I know, because my colleagues were involved, there is a protection profile been made for prepare measure QKD, has been standardized by ETSI. Yeah, and I think in the context of this Nostradamus project, a big test facility for QKD systems, they are going to, but there is a plan to also certify these systems according to the PP. If vendors are willing to do so. Yeah, so they normally get invited and have to bring their equipment and support this process. This has been done 3 or 4 times, or tried 3 or 4 times without prior to PP by the BSI, as far as I know, but nobody came.
Yeah, I think that's the current problem, that a lot of hardware manufacturer does not allow you to access the internal structure of the hardware. Thank you.